All right, I think we're recording here. Let's get started. So today is lab Y bus or building our Y bus essentially. And again, we sort of introduced the concept of a Y bus in our last class. And the whole purpose of Y bus is to be able to replicate our system. And it can be incredibly complicated and most likely will be very complicated in sort of one very, very neat and tidy matrix. And so it's used in almost every power systems analysis application and a lot of theory on how to do fault analysis or how to do voltage analyses. All those different things are developed by knowing what Y bus is. And it's probably the most basic but most essential thing to be able to convert your system into a bunch of one lines and squiggles and all this thing into a very direct, sort of basic thing that you can actually access. And so we have a step-by-step procedure here, right? Which is, it's only 7 steps, but it literally is plug and chug, turn the crank, plug and chug, turn the crank. So always got to identify the bus and nodes. And it's really important to identify the buses or nodes on your diagram. Reason why you need to do that is because when I'm saying Y bus 1, I need to know where bus 1 is, okay? Or bus 2 or bus 3, et cetera, et cetera. If I didn't specify my bus numbers, then I could pretty quickly get completely confused as to how I'm trying to go ahead and solve for my network. Then if I have any voltage sources, I want to convert those to current sources. And the reason why I convert those to current sources is because I'm trying to calculate all the voltages at all the buses. So I need to know what the current injections are to be able to calculate what that is. So just do a Norton equivalent to be able to get that. Now I'm going to convert all impedances to admittances. And this should be a caveat here, right? I don't complete this step if I have impedances that are in series with each other. So we'll add except series impedances, right? And what we talked about in our last class is if we have elements that are in series, we can't invert them and then add them because that's essentially adding them like they're in parallel. No, our very first step is to put them in series, add them together, and invert that. So make sure when you look at item number 3, you think in the back of your mind how I need to go ahead and do that. Okay. And we'll talk about how that step there's a sneaky way to doing that step here in a minute. Number 4, if we're looking for the self Y bus or the self admittance terms, we're just going to sum all those admittances that contact the bus. Even those admittances that go to the reference bus, like if you have a generator, then that doesn't go, the generator only connects to bus 2, for example. It doesn't connect between bus 1 and bus 2. It just goes to bus 2. So that admittance going to the reference bus is only going to show up in your bus 2 self-admittance step. Then we move on to step 5 is they're going to take the negative of all the transfer admittances, which is the admittances between each bus. And then those are just going to be plugged into the corresponding spot. So Y bus 2, 4 is the negative of the actual transfer admittance between bus 2 and 4. Okay. So the terminology might get a little confusing because there's Y bus 2, 4 versus the transfer admittance between bus 2 and 4. Okay. Seems like a lot of buses and admittances, but you got to be very specific in the terminology because you will get tripped up and use the wrong terms. Those are only going to show up in the upper triangular matrix. You can certainly put them in the lower triangular matrix, but this is a symmetrical matrix, which means the rows and the columns are the same. So once you build the upper portion, the upper triangle of your matrix, you have the lower triangle as long as you use the concept of symmetry or a transpose. And then you just keep repeating and repeating and repeating until you build your full Y bus. And then this last step is find the bus voltages. How do you find it? V equals Y inverse times I. Your I matrix is your matrix of all those current injections at the buses. Your Y is the Y bus, and your V is all the voltages at the bus. Now, computer programs, they do this all the time. Like if you were to use, and I use the program, I used to use it a lot more. It's called Aspen One-Liner. It's like one of the big programs, at least in the Northeast, for doing fault current analysis. And when you're connecting lines and you're interconnecting lines in the system, it actually behind the scenes, if you will, it'll actually connect things and build Y bus for you. So if you put a connection between bus 2 and bus 3, it'll actually start to modify its Y bus under the hood. So we look at it as a one-line diagram because we can visually interpret it, but underneath it's just building a Y bus. So if I'm doing a generator here, and I put a step-up transformer, and then I go to bus 1, remember that step number 3 where we said watch out for impedances that are in series with each other? We have a generator which has an internal impedance. Remember we talked about a generator is modeled as an ideal voltage source in series with some sort of impedance to limit the amount of current that is out of the machine. So there's an impedance there. And then the transformer also has an internal impedance with it. So these two devices would look like this. The problem is we just said these two have to sum together first before you invert them. But a computer doesn't have the ability to interpret that. So what these power system programs do, they'll insert a bus between there. They'll actually put a dummy bus between the transformer and the generator. So even though you say I've got a 5-bus system, they're actually putting in buses all throughout the system when you're interconnecting two different impedance devices. Okay. So sometimes, and the reason why I'm telling you that is because when I use a different program, it was called Power Tools for Windows. It would pick up whenever I would try to put what's called a tie line. So if you have a tie line between two buses, it would say you can't do that because that shows as a 0 impedance device, right? A tie line has essentially no impedance. And if I have a tie line between bus 1 and bus 2, and this impedance is 0, what is the admittance of an impedance that's 0? So Y equals infinity, right? How do you put infinity into a matrix? Doesn't work. So what these programs do is they actually put a really, really small impedance in there, 0.00001 or something like that, a small enough number that is not going to throw off your results because you can't have a solid connection because of the fact that you can't have a short circuit between the two. Otherwise, realistically, if you have a short circuit, is bus 1 any different than bus 2? No, they're the same. So why not call them the same bus, right? The other nice thing about building Y bus is if I look at the system over here, you can see that there's no connection between bus 1 and bus 4, right? So if I wanted to build, just for argument's sake, I wanted to build Z bus, what would you put for an impedance between bus 1 and 4? If you wanted to build Z bus. What's the transfer impedance between bus 1 and 4? Is infinity, right? There's no connection between 1 and 4. No connection electrically means it's an open circuit, right? Which means that it's an infinite impedance. So how do you put infinity into your program? You can't, right? So Z over here is equal to infinity. What does Y equal? One over infinity or 0. So if I have no direct connections between bus 1 and 4, when I'm building my Y bus, you just put in a 0, right? Very, very easy. No big deal to enter 0 in your matrix. Do that all the time. But you can't enter infinite in your impedance, in your impedance matrix. So that's another reason why we have to build Y bus. You just can't do the math. All right. So any questions on this system here? Because I'll walk you through the first system, and then you get to do the second system. Deal? Oops. I wish PDF would just make it easy when you don't have a mouse. Where's my pen? Guess I have to do it the old-fashioned way. All right, so I'm going to copy the system over to whiteboard so I don't have to rewrite it. And sorry, it's a little hard to read, but kind of a step-by-step. First, step one, identify all the buses or nodes. We know what those are. 1, 2, 3, 4. It's a 4-bus system plus a reference. And again, you don't actually have to show the reference because it's a 3-phase system. The reference bus of the system are the other 2 phases, right? So I don't actually have to show any connection over there because it may not be. In the real world, how a generator is connected, you have 3 lines that go in and then back out of the generator. And at the generator, at the neutral connection, they're tied together. So there isn't necessarily a connection to ground. Usually there is a connection to ground, but the reference is right here. This would be our reference. And so these other phases act as a reference for our generator. That's why we don't show the reference bus in almost all these single line diagram representations. We just show the one system. So we have the buses identified. Step 2 is convert voltage sources to current sources using a Norton equivalent. So we have, we'll call this is bus 1. So we have VG1 is equal to 1.1 and VG2 is equal to 1.1 as well. Now we have to include the impedance. So we have Z for generator 1 is equal to J.1 and Z generator 2 is equal to J 0.8. For doing a Norton equivalent, my current source equivalent, IG1, is just V divided by Z for both of those. Now I know what those 2 current sources are. Okay. So my diagram, I'm going to modify this to be a current source in parallel with its impedance. Okay. Both of those are going to just become current sources in parallel with impedances. All right, so now I have my current source. I have everything. Now I'm ready to go ahead and start inverting. So that's pretty easy. I just put a bunch of 1-overs here. Those are my admittances now. Okay. And so now I'm ready to start building my Y bus. There's no more steps that I need to do other than just start the process. So I'm going to call this Y bus, and this is going to be in row 1, column 1. So 1, 1. And that's going to be equal to the sum of all the admittances connected to bus 1. So it's 1 over J1 plus 1 over J.4 plus 1 over J.2. All right. Now I'll follow the step-by-step process, but you don't have to follow the step-by-step. The step-by-step was do all the self-admittances. So now we're going to do bus 2, 2, the Y bus. And that's going to be equal to everything connected to bus 2. So 1 over J.8 plus 1 over J.4 plus 1 over J.2. Let me know if I'm going too fast. Y bus 3 3. That's just going to be equal to the sum of the admittances connected to bus 3. So I have 1 over j point 2 plus 1 over j point 2 plus 1 over j point 08. And then my last one, bus 4. So that's 4 comma 4 is equal to 1 over j point 08. You will note there is not a single negative term in there. I'm not subtracting anything. I'm just adding all the terms together. Right? So you literally just add them up. Don't subtract anything. They're always being added. If you have a negative term in your y bus, it's because of the fact that 1 over j is equal to minus j, right? So you will end up with a bunch of negative terms in your y bus. In fact, most of the time in this class, your diagonals are going to be negative numbers or have a negative j term at the very least. But that's okay, because when I invert my j term, it becomes a negative j term. Okay? Now I'm going to build all the other elements, and I'm only going to build the upper triangle. So that's y bus of 1, comma 2. What does that equal? It just equals the negative of the transfer admittance between bus 1 and 2. So notice I called it y bus of 1, comma 2. It then equals negative y12. So the terminology that we've been using, I'm trying to call it like it actually, or what you would find if you were in the real world. We just have y bus 1, 2 equals to negative y12, not y of 1, 2. It's y12. And then we do y bus 1, comma 3. That's equal to the negative of y13. Now, I'm going to look at y14, and you can see that there's no direct connection. So that means it's equal to 0. There is a y14, right? y14 is infinity. We just said that in class, right? That there's no direct connection. So that means it has an infinite impedance. And when we invert an infinite number, we end up with 0. So you do actually have a y bus 14. It just so happens to be equal to 0. Do not forget that that term has to be entered as a 0. If you try to enter a matrix without all the numbers, you're going to find that you have some issues there. All right, so that's it for row 1. Now I'm going to go on to row 2. And I'm not going to do 1, comma 2 because I'm only looking for the upper triangle of my matrix. y21 is in the lower triangle, so I only need the upper triangle. So y bus of 2, comma 3, not 2, comma 1, because I've already got y21, it's the lower triangle. I've already got y22, it's the self-admittance. So now all I need is y23. That's equal to the negative of y23. And y bus of 2, comma 4, there's no direct connection, is going to be equal to 0. That's it. I'm done with bus 2. I don't have any more buses to work with, so I don't have any more transfer admittances. Now I'm going to move on to bus 3. Not having to do 3, comma 1 or 3, comma 2. Those are in the lower triangular. I've already got y bus 3, comma 3. So all I need is 3, comma 4, which is the negative of y3/4. Okay. And do I need to do anything with y bus with the row 4 elements? No, because that's all lower triangular, right? Or it's the self-admittance. So I already have y41, y42, y43, and y44. That's all spelled out. So now I can actually show my y bus. This is y bus 1, comma 1, y bus 1, comma 2, y bus 1, comma 3, and y bus 1, comma 4. This is y bus. And I'm just going to write this down. You don't need to write this down. So it technically, when I wrote y bus 1, comma 2 on that first row, second row, first column, that actually technically is y bus 2, comma 1 if you're just using the dimensions of the matrices. But because they're the same number, I actually don't have to differentiate those. I can call them the same number. So this is y bus 2, comma 2, y bus 2, comma 3, and y bus 2, comma 4. I already know this one, lower triangular. So now I'm just populating like crazy. And that's my Y bus matrix. What's that? Nope, that's Y bus. When I calculate is when I invert it. I do not invert Y bus until I'm doing calculations. So your Y bus, you're done. This is Y bus. There's no inversion necessary. Now, because Rita's a step ahead of us, I'm going to invert it and multiply it by my current injection. Make sense? Don't make sense? Let's see if this is right. Let us go to MATLAB. Here's our Y bus lab. And if you look closely, you'll see all the work that I did, right? So I've got X1, X2, X3. I've got all the X values just entered in, right? Those are just the actual impedance values. I call them I, but you can certainly call them J if you want. It's totally up to you. The reason why I call them I in here is if you use the term I, you can just go 4I or 0.4I. Like MATLAB is smart enough to know that you put the number out front, it knows to multiply it. So it just makes it a little bit more efficient when you write it. But that's it. That's all I had to do. Now I'm going to go ahead and show you I built all my Y bus terms. Well, I inverted them first, then I built my Y bus terms. So you can see I did those individually. I put in my voltages here, V1, V2, they're the same value. I solved for my current injections. And notice I got a little sneaky here. I said it's V divided by Z. Isn't that the same thing as saying V times Y? It's the same thing, right? Because Y is 1 over Z. So I could have done either one. Over here on line 15, I could have done V1 time or divided by Z1, because I have that here, X1. But I just said, hey, let's use admittances because it makes it easier for us. It's already there calculated. So let's just go ahead and do that. Then I just put it into my I matrix, and then I just did V bus equals the inverse of Y bus times I bus. And then I'm going to display the results. Anybody have any questions on what I'm doing here? Again, you don't have to be a MATLAB expert, but remember how I said nothing up my hands, nothing up my sleeves? You can see here, clear CLC. That means that's the first step that's running in MATLAB. So anything that processes out from MATLAB, hopefully is what we expect it to be, correct? Because there's no preset variables. I'm not being sneaky. I'm just going to run it and go that way. Anybody want to see it run? Or see the results? You don't actually get to see it run. So let's run it. No beeps. It's usually a good sign. Uh-oh. I thought we were going to get good results. It's 1.1 at an angle of 0 the whole way through. That can't be right. Anybody see a mistake? I don't see a mistake. So is circuit theory not working? So maybe there isn't a mistake. We're all engineers in training, right? So 1.1 at an angle of 0 across the board. Should it be that way? Why not? Well, everybody has this like inner feeling like, I've got a system with a bunch of connections in here, and how can all the voltages be exactly the same? Doesn't make any sense. It's almost like the system is unloaded. It is powered, but you get 1.1 at an angle of 0. It's unloaded system, right? How much load is on the system? You don't see anything going. You see connections between the bus, but the voltage sources all have the same magnitude and angle, so they're not going to act as a load to each other. Is there any load going out onto the system? No, all these buses are just energized. They're not, there's nothing sneaky going on, so it's an unloaded system. So they all should be 1.1 at an angle of 0. It should be that case. If I want to throw some load onto the system, how do I do that? Well, for me, what I would do is, you see what it says Y bus 4, 4. Let's add a 1 ohm resistor there. Right? And it is 1 over 1, right, is equal to 1. So when I invert it, it's still a 1 ohm, and we're just adding it. So essentially all I did was I'm going to put a load here, correct? I'm not going to put it in between two buses because that's just another impedance between the two. I'm actually going to stick a 1 ohm resistor in here. So that's equal to R, and 1 over R, which is equal to Y, is still 1, isn't it? So let's run that. Now the voltages are changed because you actually have a load on the system. And the way this system works out is it actually is telling you where the power flow is coming from. And it's all based on whichever has essentially the higher magnitude voltage tends to have a lower load, right? So you can see 0.947, that's going to be providing more of the, it's going to be less of it because, no, more of it because the lower the voltage means the bigger the voltage drop, right? So that is where you're going to see that you have more of the power coming out. So all you have to do is add a load. Add a 1 ohm resistor, whatever, you get different results. But going back to our previous example, we didn't have a load, so all the voltages are the same. And if you look at the second system, what do you know? Tacked at the end of bus 2 is something that is hanging off in the air. A J 1.5, we'll call it ohms for now, equivalent load. So we have to include the fact that there is a load there. So in the second problem, our voltages are going to be different than the first problem. Questions on anything? Okay, well, lab is supposed to be an opportunity for you to learn and work, right? So I babbled up here for a little bit to kind of see how to go through the lab. It's up to you now to go ahead and do all the stuff. I'm going to pause the video because I'm going to just be answering questions and walking around the class and helping people out. But if you have a question and if enough people have the same question, I might restart the video so that way we can all, be on the same page. And it's up to you if you want to do it like I did in MATLAB. You're welcome to use whatever. I don't necessarily care. You'll just find that at some point it's going to be more efficient to do stuff in that lab, in my opinion, than it is to do it on your calculator. But with that, I will pause the recording unless there's any questions from TV land. Nothing? Okay. All right. You can all get started on your lab.